talk even starts with a question. And this is actually the only non-Malta paper in this session, and
Stole a joke from me.
it will be presented by Mikael.
Okay. Hi. So this talk is about what we call a red-black planning. And actually this title is really self-explanatory. So as Anders said, if you are not interested in details, that would be a good time to go to sleep. So basically, well, we have our problem. We have this, well, we are talking about FDR problem here. And, well, when we don't relax anything, we have this piece space complete, oops, sorry. So we have this piece space complete complexity. When we relax everything, we have this polynomial complexity, and there is a huge gap in between. And, well, what happens if we relax only some of the variables? So well, the approach that we would like to call red-black planning is about exactly that. So we decide for each variable which color it will have. So some variables will get red color. It will stand for relaxed semantics. So they will accumulate their values exactly as, well, in the relaxed planning in general. Some values will get the black color, and they will get the regular semantics. Sorry? I don't really like to stand near the microphone. Okay, so we have those red variables with accumulating semantics. We have black variables with value switching semantics. And then we would like to see where our problems fall, actually. So we can play with that a little bit. Yeah, we can relax less variables, will be closer, relax more variables will be closer to the polynomial case, probably. We can relax less, we will be closer to the general case. But what is the complexity of those cases is really unclear. So that's what the paper is about, actually. Well, we are trying to investigate the complexity of red-black planning. So just some, well, really small definitions. We'll get some more later. So red-black planning is defined really similarly to FDR planning. The only difference is that now we have two sets of variables instead of one. So one will be red variables, one will be black variables. And the same, everything else is the same. The semantics is a bit different. So as I said, red will accumulate the values, blacks will change the values. So if you take an action and you apply it, well, black effects will just change the values to that effect, and red effects will add the values in the effect to the previously existing ones. Okay, so given the regular FDR task, we can take a subset of variables. Let's call them black. The rest will be red. We defined a new red-black task. So such a task would be called the red-black relaxation of the original one. And a plan for that red-black relaxation would be, well, a plan for the red-black task. And the cost of that plan will be a heuristic value. Okay? Can continue. So basically, if you take the empty set to be black variables, you got all of them relaxed. So that would be H plus. If you got the set of all variables to be black, you got the H star. So we can actually vary between H plus and H star. Okay, an example. So that's job example. You have a robot here that can move between the cells. In each cell, and in some cells, you have some jobs to do. You have to perform those jobs in sequence. So you perform job 1 first, then job 2, then job 3, so on. So you have to be there in order to perform the job. So what would be the plan? You just go to 7, perform job 1, go to 3, perform job 2, and so on and so on. So the cost of an optimal plan would be 30. For the relaxed plan, you actually have to go once all the way to 7, and then you are everywhere. So you can just perform the jobs in sequence without moving the robot anymore. Okay? Well, let's assume that we are selecting the robot variable to be black, and the rest will be red. Then what will happen is that you actually have to change the value of the robot every time that you need to go to the next job. So the red-black plan in this case, for this particular set of black variables, will be exactly, the optimal plan. Optimal red-black plan will be exactly the optimal plan. So we'll get the cost of 30. Well, we are not inventing anything new here, right? People try to unrelax some of the variables or keep to account for some additional changes of the variable. And there are several works that I want to mention here by Marie and Derek and by Emil and Hector. I don't see Hector, but yeah, thanks. That's more or less so. What they're trying to do, more or less, see if there are no side effects of those changes of some variable, and then you can just do a TSP. So in this case, if note that actually H plus already does TSP, so you'll get the same H plus value as before. Okay, so just to remind some of you that don't remember what causal graphs are, probably none of those, but well. Okay, so causal graphs, they reflect some causal dependency between variables in the problem, and they have the nodes of the causal graphs are the variables of the problem, and there is an edge from variable x to y if there is some action that changes the value of y depending on some value of x. So that's gonna be the causal graph of our running example, and black causal graph is just some subgraph of the causal graph defined by the set of black variables. So in the example that I mentioned before, the black causal graph will be just the singleton R here. Okay? So finally we come to the complexity investigation. So the interesting stuff. Okay, so what's going on with red-black planing? What can we actually say about it? Well, in this table, and I was told that I have to have a table in each presentation, right? One table. So I have exactly one table, and here we have variables. Here you have variable domains. So in the first case that we actually investigated, what happens if you have only one black variable and the rest are red? Well, it turned out to be NP complete. But, there is some hope yet. So if you actually bound the domain of that variable, you will get a polynomial case. Okay, that's great, but what happens if you actually bound the domains of many variables? If you bound the domains, do you actually have to restrict yourself to one variable? The answer is yes, because if you don't bound the domains and you have lots of black variables, of n black variables, then you actually boil up to strips planing, right? And okay, strips are p-space complete, so that's p-space complete. And interesting observation actually that we had that, well, it remains NP complete even if you have no edges in your black causal graph. So if all your black variables are disconnected, it will still be incomplete. Okay, so we have one polynomial result. The problem with that polynomial result is that it's actually exponential in the product of the domains, of the black domains. And that's, well, bounded, but not really practical. So, well, there is a paper by Yubi Chen and Omar Gimenez that says that we actually have to, well, we have to look beyond the structure of the causal graph. So we have to restrict our problem more than that. So, and they talk about the notion of reversibility. So for FDR, reversibility says that we actually can get back to the initial state from any reachable state. Okay? So once you can move from the initial state to some state, you will definitely be able to come back to the initial state. That's a strong notion. So what does it mean in red-black plane? Actually, in the red-black plane, since you accumulate the red values, it will mean that you will have to take your black values back to the initial state. And red will, well, you can only get more red values. So, they had a theorem, really nice theorem, that says that, well, if you look at your causal graph and your strongly connected components of the causal graph are bounded, then plane generation for reversible FDR tasks is polytime solvable. And if not, well, then plane existence is not decidable in polynomial time. So we actually we found a really similar result. The only difference is that here we actually talk about plane existence and not plane generation. So if strongly connected components of your black causal graph, you can disregard the red variables, sorry. And if the strongly connected components of your black causal graph are bounded, then plane existence is for reversible red-black tasks is decidable in polynomial time. And otherwise, it's not. So, well, yeah, there is an open question here, right? Don't know what happens with plane generation. But you are welcome to attack it, and let's see who will be there first. Okay, so I just want to prove, well, I will not, do I have time? Okay, so I will, 5 minutes? 7? Wow. Okay, so I will kind of prove it. I'm not going to be formal till the end, but I will try to give you the intuition that why is that correct. So the first observation is that, well, the reversibility doesn't change if you take some variables and glue them together. So if you have bounded strongly connected components, you can make one variable out of each component, and the reversibility of that task will remain the same. And that means that you actually can look only on tasks with directed cyclic causal graphs, black causal graphs. So that's actually our next theorem that says that, well, for reversible red-black tasks with acyclic black causal graphs, well, they are solvable if and only if their delete relaxation is solvable. Right? Okay. So delete relaxation, well, if the delete relaxation is solvable or not is easily checkable in polynomial time, right? So, okay, so the proof based on 3 lemmas. I will briefly mention them now, and I'll explain each of them in separate. So the first one is that, well, since we are talking about plane existence and not plane generation, we can actually well, assume that we can reach all the reachable in the problem red values up front. And then just forget about the red variables. And the second one says that, well, if your black causal graph is acyclic, then you have some topological ordering of black variables from root to leaves, from roots to leaves. And once you get to some state, you can actually revert back to initial state only subset of the, well, top variables in that order and leave the rest untucked. That's, okay, that's pretty simple, right? You don't actually need those values for changing the upper ones. And the third observation is, okay, I will be brief here. So, well, maybe I'll actually want to go to those observations and explain them in detail. So the first one is really simple. So you get to state. The first reachable state, go back, next, next, so on, and so on. Every reachable state, you just go there, you go back, and you only increase your red values, and, well, black remains the same as in the initial state. So you go back, and when you are done with all the reachable states, you have all the red values that can be reached in the problem. The second observation is well, the following. So we can actually tick our red variables, say, well, they got their goal values. They accumulated all the values that we're going to need in the black, well, in the actions that change black variables, and we can just put them aside. So that's not necessarily that those red variables are upper in the hierarchy of the causal graph, but we just put them aside. And here we have the black variables in the order of their, in their topological order in the causal graph. So once we, so we start from this state, from the initial state, we go to a new one with different values, and then we can actually revert to a state that will have upper values as in the initial state and the lower values as in this reachable state. Okay? That's fairly simple. So we'll use it for the last lemma, and last lemma says that, well, if we have a relaxed plan and it achieves some black values along this plan, let's assume that we want to get that black value from that variable and that value from that variable, and it was achieved somewhere along the plan. So our relaxed plan ends up and it accumulated that, those values. So for each such a subset of values that is a partial state, we can achieve this partial state by a red-black plan. And it goes as follows. So you have your relaxed plan, and we're going to use it in order to build our red-black plan. So assume that we have an action 4 that achieves the last goal value G4. That's our lowest goal value. So since, well, that's an inductive proof. So since we have a relaxed plan that ends with A4, the preconditions of the action A4 are achievable by a red-black sequence of actions. So there is a red-black sequence of actions that ends with A4. Applicable red-black sequence of actions that ends with A4. And then what we do is apply it and revert back to the goal, everything but G4. Okay? So we can continue as follows in the same way, and we tick our goals one by one. That's it. So that finishes the proof. We have so we have our relaxed plane that can, well, we know that for DAGs, with reversible red-black planning tasks. We can check whether red-black plan exists by just checking whether a relaxed plan exists. That's it. So the summary. So previous work accounted was rather limited in accounting for, well, change in values. This way we can actually pretty easily interpolate between relaxed planning and regular planning. And well, here we have only plan existence tractability results, but there are follow-up papers that actually have plan generation fragments for similar, well, with some extended criteria. And well, there is huge amount of work to do in red-black planning. We invite each of you to join us. Thank you.